Thanks for coming in such a huge amount today. Just for the archives, because I think everybody knows my name. My name is Leon Petkov. I'm the former research fellow of the IEC in the field of plasma physics and space propulsion. And it's a great pleasure to introduce today the final presentation of the Ariadne study, which dealt with the kinetic modeling and simulation of IEC devices. We'll hear in a minute what that was about, and of course in the technical talk afterwards, more details about what was done. And let me also introduce the guest today from the University of Stuttgart, IRS Institute of Space Systems. Speaker today, Dr. Georg Hertrich, project manager at the IRS for this project, also head of electric propulsion and re-entry technology. And we have also Constanze Syring, which significantly contributed to this project. She gave significant support from an experimental point of view. She's building an IC device at the institute. The third person involved, Marcel Pfeiffer, could not join today. He made actually, well, the hands-on the simulations. So, nevertheless, we hope to be able to answer every question which will be raised. And well, I think it's time to get to the details and to the executive summary.
Thank you. Thanks for the introduction. Thanks for the invitation. We are really happy to be here. And before I start, I have to say that I very much enjoyed this project from the point of view of the manner of cooperation with the ICT. So let's say in a vivid way, you can say the project was done by the three, in particular by the two, but also by him, and this is a good thing. Yeah. Now, let's start with kinetic modeling of jet extraction mechanisms in spherical IEC devices. This puts the point. Yeah, IEC devices are, as you may know, originally from a field that you could call fusion research, where people orient a set of concentric electrodes in order to create in the center of the cathode a high density, more or less ion plasma, that dense and that rich in thermal energy that they can investigate fusion relevant processes. Now, one observation was that if with the electrode, and this is an image of the IRS device in operation, and if the electrode, in particular the outer electrode, has a disturbance in its symmetry, then you can achieve that a plasma jet exits. A plasma jet of which literature reports that it is very likely an energy-rich ion jet, together with electrons. Yeah? Before I start advertisement, I guess it's very nice for you to know that we know where we come from. Actually, when you look at IRS, you can say in Germany, IRS does anything in the field of what some people call plasma thrusters. Yeah? While other institutions rather look at ion thrusters. Yeah? Which is still as well a plasma thruster, but we don't name it like this. Yeah? And plasma thrusters means thermal arc jet up to high powers up to 100 kilowatt, and low powers 1 kilowatt, less than 1 kilowatt. Pulse plasma thrusters in a frame of a DLR contract, and applied field MPD, steady state operated 10 kilowatt and 100 kilowatt in the frame of a EU project and in the frame of a TRP from you guys. Titus, which is the hybrid device, put in series of a 100 kilowatt arc jet and an ICP, an inductively heated source, which we investigate in the frame of a German Research Foundation funded project. Yeah? And this is a cell-feed MPD of the megawatt class in steady state operation, which we investigated in the past. And as a matter of fact, we learned that these accelerations, MHD based, whatever or however good they are or not, always live from the high powers. And if you want to get rid of from the high powers, you have to apply external field, which leads you to applied field MPDs that you can operate also at powers, for example, at 10 kilowatt. This is the story. This is the work we do at IRS in combination with modeling. So we do both modeling and experiment and development. Now back to the theme. The investigation of the effects and phenomena leading to and occurring in a jet uncoupling from an IEC device was the theme. And it's clear what the ambition is. The ambition is to acknowledge that this energy-rich ion jet is more or less maybe a measure for a future propulsion system. Yeah? And now the thing is that works are rare, literature basis is rare, and when you look at it, you can say a comprehensive theoretical model of the underlying jet extraction physics is lacking. And IEC reactors with steady state extraction have been demonstrated, and some information are there, but the jet extraction needs to be understood, and that's why we tried to come up with a kinetic simulation of the particle interactions as the densities and the processes, for example the external electric field, more or less drive the theme into the modeling, making use of particle codes. That's how it is. Yeah? Now, from the principle, you can have different or diversity of electrode combinations. We at IRS work with a 2-electrode system. Yeah? And what we do is the following. You have a center cathode and an external anode, and you have the tank at the first stage flooded with the propellant. This is of course a preliminary stage. Later on, of course, you will attempt to hermetically close the anode and to feed the system with a defined mass flow rate. Yeah, but this is the first stage. And what happens? You ignite, if you do not use an external plasma source, you more or less ignite discharge, and the charged particles experience a certain orientation from the fact of the polarization of the electrodes. But what happens is that if you have this asymmetric opening in the outer grid, that you get very likely certain gradients of the electrical potential that more or less may behave or feature like an electrostatic loss. Yeah? So, what can I say still? What stands on the slide, which I didn't say? Nothing, except for the fact that ions, of course, may behave differently. Ions have their movement firstly towards the cathode, but for ions that have a significant thermal energy, they may cross and swing back and forth and are catched in the center of the cathode due to the potential. Yeah? And this creates this potential to have an energy-rich centered plasma. Yeah? Okay. Now the framework that we used, or that we planned to use initially, was a complex code system that had been developed at IRS, Karlsruhe, the KIT, the High Performance Computing Center in Stuttgart, and the IHE in Stuttgart, which is a combination of a Fokker-Planck solver coping with the Coulomb collisions, a DSMC solver coping with the neutral charge-neutral collisions, neutral collisions, and a Maxwell-Maslow, or let's say a P code, you can say. Yeah? And in the most general way, you would say that you need to have all of the 3 different subcodes in order to cope with the, let's say, majority of the plasma physical effects. Yeah? This is how you can say it. But when we started working, and don't be shocked by the table, I'll just tell you some scratches from the table. When you start with the work, you easily learn that you have to have a very huge amount of preparatory activities. Preparatory activities that just come from the fact that the IEC is too unknown. Yeah? And that experience in the field is too unknown because there has never ever been a 3D simulation of an IEC. Yeah, that's the point. So what we have to do